All right, this next video follows our VSEPR intro where we are looking at how you can determine what the shapes of each of our molecules are. We are looking at the steric number for these elements right here. Okay, a steric number of 2 means that you have 2 things around the central atom, so they can be either linear or just linear, because 180 degrees is the max they can get away. 3 things around the central atom is trigonal planar or bent or angular, if one of them is a lone pair. And 4 things around the central atom is tetrahedral, 109.5 degrees. One of them is a lone pair, it's a trigonal pyramid, and 2 things around it is going to be a bent or angular. You don't need to know the 5 or 6 ones right here. So, what we do with our VSEPR theory in order to accurately predict the shape of these molecules, you're going to draw your Lewis dot structure. You're going to count the number of atoms around the central atom and how many paired of unshared electrons they have, and then you're going to try to figure out what the steric total number is, and then the shape is derived from that exact steric number. Okay, so you'll be referring back to that. So let's take a look at the VSEPR shapes for these things right here. All right, so we have HCl, that's our hydrochloric acid. Okay, we have an H and we have a Cl. Okay, well, there's only really one way to draw these, and that is with a connected line between them. There's one thing that it is bonded to. This is definitely a linear shape. It doesn't technically have an angle because an angle is 180, or is defined as 3 different things. Okay, having an angle like so. Okay, but you do see that it has a linear shape. Okay, cyanide is HCN. All right, so we have hydrogen, we have a carbon, and we have a nitrogen. All right, and when we bond them together, hydrogen has 1 single bond between it and carbon, leaving 3 bonds left for hydrogen, 3 bonds left for nitrogen. So we're going to show a triple bond between them. And what you'll see is my central atom is carbon. There are 2 things bonded to it. So the furthest that this can get away from one another is 180 degrees. This has a steric number of 2, and its shape is linear. Good. Next we have PCl3. Phosphorus has 5 dots. Chlorine has 7, or a dot and 3 lone pairs. So it looks like so. And then they are bonded to one another. So how many things are around our phosphorus central atom? 1, whoops, I wanted to use a different color there. There is 1, 2, 3, 4. There is a steric number of 4. How many lone pairs? There's 1. So that means this is a trigonal pyramid, and the bond angle is less than 109.5 degrees. All right, what about CBr4? We have carbon, and then we have 4 dots around the carbon, and then we have bromine, which has 7 dots on each one. And then let's show them all linked up together. All right, how many things are around the central atom? 1, 2, 3, 4. Steric number of 4. Any lone pairs around the central atom? Nope. So this is tetrahedral, and the bond angle is 109.5 degrees. All right, and this is what our substances would look like. Here is our HCl. Here's our HCN, PCl3, and this is CBr4. So you'll see these guys are linear. This is a trigonal pyramid. This is a tetrahedral shape. All right, in my notes and on the website are these different build a molecule simulators from PhET Colorado. So I would definitely take a look at them because they definitely help see what all these look like and how their positions change. All right, so one of the things that we want to look at here is the molecular geometry and show the bond angle as well. And I think this really helps view what's going on here. All right, so if we have just two things bonded to one another, it's a linear shape. It doesn't really matter how it's positioned. There's no angle because there's not three things there. Okay, but if we add another, no matter how hard I try to push them together, these two things repel one another and give you that bond angle of 180 degrees. There's no lone pairs around it, so you'll see that it's going to maintain that 180 degrees. If I have a steric number of three things around the lone pair, notice these are all in the same plane, PLANE. All right, and they have that bond angle of 120 degrees. Beautifully done. But if I remove one of these bonds and replace it with a lone pair, it's going to still give me this bond angle that started with that trigonal planar shape. Okay, and that's the electron geometry of the whole thing. All right, so four things around the central atom is going to be a bond angle of 109.5 degrees. Notice it is definitely not 90. It's more than 90. You can see how this thing is coming towards us and these others are going away, and they show you the exact geometries of those. All right, if I get rid of one but replace it with a lone pair, you see the difference between the tetrahedral shape and that trigonal pyramid and trigonal planar. No lone pair, they're all in the same plane. One lone pair, they get repelled down. Okay, look at that again. No lone pairs, lone pair. Steric number of 3, steric number of 4. Okay, if I remove one of these and add another lone pair, here is your bent or angular bond angle right here. Okay, so always very nice to see this stuff with the simulator. Okay, the real molecules that you want to look at would be like that of water. You can see your molecular and electronic geometry showing that even though I have these lone pairs here, these lone pairs push this bond angle to exactly 104.5. If we look at methane where they aren't lone pairs, you'll see that they are 109.5. Your, where are you? Ammonia, NH3 has a bond angle of 107.8 because it has this lone pair here, giving it that trigonal pyramidal shape, which really does show us the lone pair definitely factoring in up here. And something like CO2, no matter how I spin it, even though there are 4 things, it's not actually a difference between the atoms that are bonded to it. So there's really 2 atoms bonded 4 ways. SO2 has that lone pair. BF3 is going to be that trigonal planar. CLF3, this goes down into the other guys. All right, so hopefully that helps us see exactly what's going on in all of our different shapes.